All right, this is day 11. We're going to start Unit 4 today. We're going to start with 4.1. Some of these things that we see today are going to be very familiar to you. There's some middle school concepts. We're going to work our way up through some more Algebra 1 and then some Algebra 2. And then eventually, as we get through the unit, we'll segue into our geometry counterpart. But the way we're going to start here is we're going to do a little visual activity just to kind of segue into the types of concepts that we're going to deal with here at the beginning of Unit 4. So looking at the screen, we have a picture here. Here we have Michael Scott. And Michael Scott is a smaller version of a picture. Now, we want to try and fit Michael Scott into one of these frames. Now, we're familiar with these frames, an 8 by 10 size picture, 5 by 7 size picture. Maybe the one we have in our hand here is a wallet size picture. So if I was to drag this picture here, obviously it's not going to fit in either of these frames right now. But what if I was to make it bigger? Now, if I was to make it bigger, I could do it a couple different ways. Maybe I try and stretch it out this way, and then stretch it out this way. If we do it this way, what we're doing is we're distorting the picture. That is not a very appealing way to grow a picture. One, because right now I've gone too wide. This picture has grown left to right, so it's grown horizontally more than it's grown vertically. And I can keep tinkering with this to see, is that perfect right there? Now, it might look perfect, but maybe if we were to show this to Steve Carell, Michael Scott, he might think otherwise. I'm going to go back. And now you might know if I hold in Shift and drag from the corner, now both dimensions, and you can see the size of the picture right there, are growing at the same rate. Or we would say that they are growing proportionally. So I can look at those numbers. Will those numbers ever hit 8 by 10 exactly? Or if I was to put it down here in the corner and drag it, is it going to fill up this frame perfectly? And we see that it does not. Notice how it falls short. It maxes out top to bottom, and it leaves all this extra space on the right. I could center that if I want to. You might see something like that on your TV. If you're watching a standard definition image on a widescreen television, a high-def television, you have those bars on the side. And that's why the picture is not the same. We call that an aspect ratio, and that's kind of the keyword that we're getting at here. Another keyword is this picture growing proportionally to fit an 8 by 10? Meaning, is this picture just a mini version of an 8 by 10? And we've shown it is not. And the reason we know that is because it doesn't fit perfectly. That corner did not go into that corner perfectly. Now, if I take it over to the 5 by 7 and grow it, maybe we're doubling the size, we've tripled the size, we've quadrupled the size, and here we see that it fits perfectly. So this original picture was a miniature version of a 5 by 7. We just had to scale the picture up by a couple factors. Maybe we doubled it, we tripled it. Maybe we increased the size by 4.5. The key was when we increase it by 4.5 or by 5, we increase both horizontal and vertical by the same factor. Okay, over here to fill up this frame, we would have had to maybe triple the width and maybe quadruple the height of the picture. Now that might look good to our eye, but mathematically, it is distorted. Okay, and maybe if you were to ask the person who took the picture or even the subject of the picture, they would say it's distorted as well. So what we're going to talk about is ratios. So we couldn't do that activity together in class, so we had to do it just visually on the computer. So what is a ratio? A ratio is a comparison of two quantities. So in that picture example, the two quantities were horizontal and vertical dimensions, length and width, 8 by 10. So there's 4 ways we can represent that. And be prepared to be able to answer this question later on. 4 ways to represent a ratio. Okay, one way is a colon, maybe 8 to 10. And the order matters. The 8 before the 10 is different than if we were to flip-flop those. Think about a landscape versus a portrait picture. We can turn that into a fraction. Now you might be thinking, well, we can simplify that. A fraction is a fraction. That's one way to represent it. A decimal, which is 0.80 or just 0.8. And then a percent. Now a percent, we move the decimal place over twice. So 80%. 8 out of 10, 80 out of 100. So 8% or 80%. If we were to set two ratios equal together, we would call that a proportion. And that's the key word that we're really going to focus on. Because that's what we just did visually in that little activity there. We wanted to know if that little picture of Michael Scott, Steve Carell, was it proportional to an 8 by 10? Was it proportional to a 5 by 7? And there's 2 ways we can verify that. We can compare the simplified fractions, or we can compare the decimals. Or, and here's what we're going to focus on the most, we can look at their cross products. And here's what I mean. Let's say I have 3 over 6 as a fraction. That is a ratio. We don't know what that represents. We don't know what the 3 represents. We don't know what the 6 represents, but it is a ratio. If I was to set it equal to another ratio, they don't look alike, but do they represent the same ratio? So when I said middle school, this goes back even before middle school. Are those indeed the same thing? You should be saying yes. 3 over 6 is a scaled up version of 1 over 2 because we just multiplied the top and bottom by the same factor. That's what I meant by scaling up that picture. We are multiplying the horizontal and the vertical maybe by 3. Here we tripled it. If the picture was 1 by 2, now it's 3 by 6. Nothing was distorted because they both grew by the same factor. So we can compare their fractions just by dividing them. Or the other option would be to do cross products. 6 and 1. So 6 times 1 Does it equal 3 times 2? And it doesn't matter which one you do first. So change both fractions into decimals, cross products. Now, obviously, the decimal was much easier, but this is going to be our strategy when it comes time for our algebraic ones. So if you're familiar with these numbers at all, this is basically the resolution of a high definition image, 1080 by 1920. You have 720, you have 480. You have something that goes up to 4K. But basically, this is the dimensions of the screen on your phone, the television that you watch, and most of the things that you watch. All the widescreen televisions and your phone, even though all our phones are different sizes, your phone's much smaller than your TV screen, they all have a screen ratio of not 5 by 7 or 8 by 10, but 16:9, meaning it is 16 wide by 9 high. Now, that doesn't mean that your phone is 16 inches by 9 inches or 16 centimeters by 9 centimeters, but it is some scaled down factor of that. Or your TV or the Jumbotron at your favorite stadium is a scaled up version of 16:9. Now, they don't all follow that, but most of them follow that aspect ratio. When you go to the movie theater, that screen is even a wider screen than a 16:9. So if we take this image that's this size, will it fit on a TV screen that is 16 by 9? So we can divide both of those out, or we can do our cross products. So on your calculator, you can do 16 divided by 9. And is that the same decimal as 1920 divided by 1080? Or we can do the cross products. 9 times 1920 . 16 times 1080. Which is 17,280 equals 17,280. So that means that that picture, that image, would fit on that television and nothing would be left over. Like I mentioned earlier, if you're watching a standard definition video or a low budget commercial on your widescreen television, you have those vertical bars of leftover space on the top, left and right. Or it might be the other direction. Maybe you have some space at the top and the bottom when you're watching a movie on your television. So basically, when the aspect ratio of the picture doesn't match up to the screen, we have some cropping that gets involved, which happens whenever you try and post a picture on Instagram. It kind of forces you into a 1:1 crop versus what your picture has been taken at, which tends to be a problem. So let's look at the next one. This is still dealing, if you're familiar with these types of numbers, 720 by 1280. Again, it's the lowest form of high definition. Here is like DVD quality. Okay, 480p, 720p. You might see those on your YouTube settings if you're changing the quality of your video. So is this just a smaller version of this? So if we do our cross products, let's use a color there. Doesn't matter which one you do first. 640 times 720. We get 460,800. And then 480 times 1280 is 614,400. So those are not proportional. If we simplified them both down to 2 decimals, they would not be the same decibel, which means that this image, just like Michael Scott in the 8x10, would not scale up to fit in this image perfectly. And the reason I keep talking about images is because they're rectangles, and that's going to help us as we get into our geometric component of this. All right, so let's get into the algebraic versions of this. Now, the reason why we are practicing our cross products is if we do not know one of the 4, and you have to know the other 3, you can only have one that's missing. Meaning if I have, let's say, a picture that's 3x8, and I want to scale it up so that the shorter side turns into 63, what does the longer side have to turn into so that the image does not distort? So basically, it's a bigger version of the 3x8. Now you can play around with that and say, well, what did we multiply 3 by to get 63? We have to multiply 8 by the same thing. That's fine if it's a nice whole number, but if it's a decimal, you're not going to want to go that route. This will take care of that for you. 8 times 63, 3 times x. So 3 times x is 3x. And then 8 times 63, 504. Divide by both sides by 3. 168. So if the 3 is going to scale up to 63, that means the 8 has to grow to be 168 for this to still be proportional. All right, as they become more algebraic, they might lose their context. It might be a little bit harder for us to refer to a picture. But the principle of what we're doing does not change. Now, I recommend putting parentheses around these expressions because when you multiply 7 by that, you have to multiply the entire thing. So we will have to distribute. That's 7x minus 21 equals 12x plus 6. Let's take our time algebraically here. Let's get our x's on the same side. Doesn't matter if you take the 12x to the other side. That's negative 21 equals 5x plus 6. Subtract 6 from both sides. We get negative 27 equals 5x. Divide both sides by 5. X equals negative 5.4. And we keep going. Here we have an x down here and an x up top. So that's 36 times 12 equals 2x times 6x which is 432. And now let's be careful. 2x times 6x is 12x squared. So this has now become quadratic. Now it's not that scary of a quadratic because we can just divide this by 12 on both sides. Which gives us 36. And just like at the end of the Pythagorean theorem, to get x by itself, we're going to take the square root of both sides. So x equals 6. And don't forget, there's going to be two answers with a quadratic. X is -6. Reason being, 6 times 6 is 36. -6 times -6 is also 36. All right, 5 times 4. X plus 2 times x plus 3. That gives us 20 equals. Now this time, we have to FOIL this. So think back to the end of Unit 2. I believe it was section 2.7 when we did the quadratic problems with that rectangle, and we did a lot of them. This should look very familiar at this point. When we FOIL this, we should get x squared plus 3x plus 2x plus 6, x squared plus 5x plus 6. To solve this type of quadratic, we need to get it equal to 0. Minus 14. And then this is the point that we would go to our calculator. Now, you might not have a calculator on you. Maybe you didn't download the TI software that's available now that's free. But you can just go to Desmos if you'd like. Remember, when we graph this, we know the solution that we're looking for is at the x-intercepts. So I'll put a link up to the Desmos so you guys can use that. But essentially, you're just going to type it in right here. Y equals x squared plus 5x minus 14. And we have 2 and -7. So x equals -7, x equals 2. We used to cross out the negative one. We really don't know what these represent, so we're just going to keep them both. All right, 4.1, there's going to be a 4.1 part B for tomorrow, but I want you guys just to focus on these algebraic properties. This cross product, really just, that's going to be a really important part of what we do from here on out. So I want you guys to just get practice with that. Make sure you guys take a look at the homework and make sure that you're getting back to me with any questions. Come to my office hours. You want to get any of this stuff cleared up at the beginning of the unit so it doesn't linger and continue to be a problem throughout Unit 4. All right then.